Hello, everyone. My name is Michael Yuan, and I work at a company called Second State. I want to talk to you about how to do AI inference on what I call the edge cloud, but mostly on a WebAssembly VM in the edge computing scenario. So let's get started. When we talk about AI and the deep learning, everyone likes to think about training a model, having the latest data sets and all that, GPT-3, people talk about how many parameters it has. However, if you look at the real world use case of AI, the training of the AI model is actually, I would say, a solved problem. It only takes 5% of the computing work. Essentially, this has become a low code or no code work. A business analyst can collect enough data and write a Python program to train a model that they like, right? For language recognition or for face recognition or things of that nature. The real challenge, the real engineering challenge for developers actually comes for deploying the AI model for inference. Inference meaning when you have an AI model and then you have some kind of input data, and then you apply the AI model to the input data to see to get some kind of results, right? So if you have a facial recognition model that was trained to recognize everybody in your household, and you put that on your door camera, that's the training part. That's actually the easy part, and the difficult part really is when someone come up to the door camera would take a picture of that or take a video of that person, and then apply that model to that video or that picture and see who's in it. And it would be able to tell whether this is one of your family members or friends or whatever, right? So that's the inference work is actually 90, 97, 95% of the AI computing work that's existing in this world. And that makes sense because because once you only train the AI once, but you use it millions of times, right? So it makes sense. It takes it takes much more engineering effort and much more work to to do inference for your AI model. However, one of the challenges of the AI inference is that as the accuracy of the model improves, like from 70% to 85%, the complexity of the model and the time required to run the model really exploded. It goes from a couple milliseconds to over 30 milliseconds. So we can see about 20% increase in accuracy. You're gonna need, say, 7%, 700% increase in computational complexity and the time it requires. So it really pays to have a highly efficient runtime to run those AI models, to run your AI inference applications, especially in the edge cloud where the computing power is constrained, the device is small. That's where WebAssembly can really help. And this is what we see one of the most important one of the important use cases of WebAssembly in the real world. So before we go further, we want to talk about what about Python? Why not Python? Because when people train their models, they typically use Python, and then they can use Python to do inference. And the official, TensorFlow serving application is a Python application. So you can certainly build a web application or service application using Python. However, Python is, in general, not very efficient, not a very efficient language. In fact, it's mostly used as an interface language, even for AI training. It's so you write the program in Python, but under the hood, the Python application actually calls C++ native application to actually do the heavy lifting of AI training and AI inference. So Python is not very efficient. It could be 4 orders of magnitude slower than similar programs that read in C. So as we have just mentioned, if the actual AI work is when you write a Python program to do a TensorFlow work or do AI work, the actual work is done in a C-based native library. However, in the inference scenario, there are also a lot of work that you have to do before and after you apply the model. So for instance, using the scenario we just have mentioned, there's a door camera with an AI model to recognize faces. The pre-processing may consist of taking the video, resize the video, and then taking keyframes from the video, and then just recognize people on that keyframe instead of recognizing every single video frame, right? And the post-processing may involve putting a box around the faces that detected on each of the frames, and put a name next to those names, and then decide what to do, right? If you see a family member, would it automatically unlock the door, or would it, if you see someone that doing something abnormal on your front porch, would the camera automatically send out an alert? Something of that nature happens after the processing. So for all those work, it's probably 90% of the work when you do AI inference work, right? That's the pre-processing and the post-processing. And to write all of them in Python is sometimes very inefficient and a waste of resources. And I have a little table here that shows the time required and the memory required for different programming languages. And you can see the Python compared with languages in C, C++, and Rust. Python is really, really slow, hundreds of times slower. And it also uses several times more in terms of memory. So if Python is not good enough, why not use native applications? For sure, native applications will deliver the highest performance for any workload that we have, right? However, we have been trying to move away from fully native application on server or on client in the past, I think in the past 20 plus years since Java came along, right? Because the native applications are tied to a specific operating system or the hardware platform. They are not portable. When Java first came out, the selling point really is write once, run anywhere. It's still the case, right? That's the portability is still a much desired feature, and it lacks integration into web or application frameworks. When you have an application framework that runs, code that's written by other developers, you typically do not want that code to be native applications, because in that case, it could crash the system, or it could cause problems with the rest of the system. You want the code to be managed. That's the whole idea of managed code, right? And it could crash. It lacks finely controlled access in terms of operating system resources. So native applications can deliver very high performance, but they goes against the software engineering advances that we have in the past years. So that's in our mind, this is not a very good alternative, from the engineering point of view. So we can't use Python. Python is too slow, and native code are too cumbersome or too unsafe to use, and that's where WebAssembly really shines. So we say WebAssembly to the rescue. And just a little advertisement for my own company. So we create one of the highest performing WebAssembly runtimes in the market. There's a paper we published on IEEE software that compares our performance with the rest of the industry. And we have recently donated this open source project as a sandbox project for the Cloud Native Computing Foundation. It's a foundation on the Linux Foundation, so that we want to see more collaboration from the community to use our open source product for the SSVM in the server side environment or in the edge computing environment. So from our point of view, we have just talked about the disadvantages of native applications. So the advantages of WebAssembly is the opposite of that. So it's high performance compared with Python. It has safety, security. It's language agnostic, and it also has a very large community. So this is what we call the product community fit, right? So there's lots of people interested in WebAssembly technology, and there's standard organizations that's working hard trying to come up with standards around this particular runtime. So from our point of view, the language Rust, which handles type safety and generally produce high performance but also safe applications, plus the WebAssembly runtime, is roughly equal to the Java programming language plus the JVM of 20 years ago. So you can roughly think of it that way. But with the Rust plus WebAssembly, the very unique benefit is that it provides very high performance compared with Java plus JVM. So so the SSVM is our open source product. It's our open source project that donated to CNCF. It's a popular WebAssembly runtime optimized for high performance applications. Check it out on GitHub and be a contributor if you are interested in this. So now let's get back to how WebAssembly solves or how WebAssembly approaches this AI inference problem. We will use TensorFlow as an example, right? So there are several different alternative approaches to run a TensorFlow model in a WebAssembly application. So the first, of course, is to run the TensorFlow model in the interpreted and WebAssembly in the interpreted mode on the CPU. So if you the TensorFlow model is actually a little program consists of many tensor operators, and the model basically describes how to transform those tensors in order to get a result from that particular model, right? So we can Google's standard TensorFlow library uses C++ to implement those operators, but we can also implement those operators in Rust and C++, and then compile the Rust application into WebAssembly. Then we use that WebAssembly to load the TensorFlow model and execute those opcode inside the TensorFlow model. And we can run this in the interpreter mode on the CPU, right? This is perhaps the most straightforward and the easiest to understand mode of how WebAssembly can execute a TensorFlow model, right? So you write the application in Rust, and the Rust application reads the TensorFlow model and interprets and executes all the operators and commands contained in that model, and then give you the results, right? So, however, the problem with that is it's very, very slow. Image recognition task takes about 10 minutes on a modern CPU for that work. So we have an example here. That's you can try out the Rust TrackQuake, which is the Rust implementation of TensorFlow, and you can compile the demo application or the sample application in WebAssembly and try it, and you will see it runs really, really slow. It takes 10 minutes to run a MobileNet model for image recognition. It takes 10 minutes for it to tell what's in an image, right? So it's clearly not really acceptable. It's useful in illustrating the concept, but not really acceptable in terms of performance. But the performance with a little optimization, the performance can be drastically improved. That's the just-in-time compilation. So it's the same thing that we have the TensorFlow operator. We write a Rust or C++ application, and then you compile it to WebAssembly, and then use the WebAssembly program to read in a TensorFlow model, and then execute the operators and commands inside the TensorFlow model. But we run it in a highly optimized just-in-time WebAssembly runtime like the V8. And now the image recognition task is 3 seconds. That's hundreds times improvements over the interpreter mode. Right? So one great example of this is Google's own TensorFlow.js. It's Google's C-based TensorFlow runtime and cross-compiled into WebAssembly, and loaded into a JavaScript application. So you can use it inside your browser, as long as the browser has WebAssembly support. And this type of application allows you to send in an image and then see the result in 2-3 seconds. That's typically okay for web application or for mobile application. You send an image, you wait a little, and you get the results, right? So that's for browser type of applications. You can do this to use just-in-time compiler and get the performance down to 2 to 3 seconds. And similarly, there is another approach, which is because like we just said, the TensorFlow model itself is a mini program. It has operators and all that. And the approach we just took is to write a WebAssembly application that reads the TensorFlow model and execute those commands. But alternatively, we can maybe we can have a compiler that compiles the entire TensorFlow model into a WebAssembly application. So we save the step to read the model. So the model itself becomes an executable application, and then we can run that application directly on any WebAssembly runtime, including GIT WebAssembly runtime, and that takes takes the average type of image recognition down to 1 to 2 seconds. So it's even faster because it saves the time to read and parse the TensorFlow model itself, right? So representative examples here include the Apache TVM project, which allows you to compile a TensorFlow model into a native application or WebAssembly application. It's also our work with Qualcomm on the ONNX compiler for WASM. So basically, we wrote a WebAssembly compiler that can turn an ONNX model into a WebAssembly application and then just run. However, the downside of this approach is that the model itself is compiled into a WebAssembly application. It's difficult to then add pre-processing and post-processing for and after the model processing, because you are talking about essentially changing the output from compiler. It's doable, but it's just not it's just a little harder and a little unnatural for developers to do that. So now let's go to how we do it, right? In SSVM, in our WebAssembly implementation. The way we use it is we use host functions. And because this is a WebAssembly conference, and I think most of us know about WASI, right? That's when WebAssembly runs inside the browser, you don't need WASI because you don't need to access operating system native functions. But when the WebAssembly runtime runs on the operating system on the server side, you need something called WASI to access the libc functions, right? Those are the file systems, the network, not the network, but the the command line arguments and things of that nature. So those are native functions that's being provided into the WebAssembly environment as host functions, and that's WASI. So we can, but if WASI can wrap around libc functions and make them available in WebAssembly, we can also have a WASI-like extension to wrap around the native TensorFlow functions and make them available as host functions inside WebAssembly, right? So essentially, the way it works is inside WebAssembly, we want to call a TensorFlow function, and we have a special API that calls the TensorFlow host function. So essentially, we are sending this data to the CBase, the native TensorFlow library, and have the native library process this request. And after the request is done, come back with the data. So essentially, we can write a complete application in Rust. The pre-processing of data is done in Rust, and the AI inference is done through a SDK command that drops down to the operating system native TensorFlow functions. And then after that native processing is done, come back to Rust and then finish the post-processing. And we compile the whole thing into WebAssembly and then run it inside SSVM. And with this, the image recognition task takes half a second. So it's 2,000 times improvement from the original interpreted mode. And that's very acceptable for, I think, for your average, for most average image-based applications, right? Either a web application or mobile application. And there's a tutorial, there's an example for that, and you can see the link on this slide. And now we can go one step further because we are already taking the WebAssembly call to TensorFlow off the WebAssembly VM into the operating system and then run it as a native command, right? So we can actually have different, different implementations of TensorFlow native libraries to handle our inference work. And so we can have a version of TensorFlow that supports the GPU, we a version of the TensorFlow library that supports specialized AI chips, like the AWS inference chip. And then on the other hand, the WebAssembly application that pre-processed and post-processed data can also be optimized by the AOT compiler. We can have the ahead of time compilation to further optimize the performance of data handling before and after the AI inference. And that would allow us to take the image recognition task to 0.05 seconds. So that's 20 frames per second. And that's in that regard, that's because live video is about 30 frames per second. So we can have almost real-time processing of a video stream, of every frame in a video stream, through by running an application like that inside WebAssembly. So one of the examples that we have is SSVM on Tencent serverless. They have GPU-based machines and all that. So there's a template application we have on GitHub, and if you're interested, you can check it out as well. So finally, I want to show you some code. That's let's see exactly how how the WASI approach works. Where is the pre-processing? Where is the host function that we use for the AI inference, and where is the post-processing? So the function here is called infer, and it's a Rust function, and which we will compile this Rust function into WebAssembly. So we'll show you the source code here, and it takes a single parameter called image data. It's an array. It's when the user submit an image, it's the application, the host application passes it to the Rust function, and this Rust function takes the image as a parameter, and it returns a value. It returns a string value. The string value contains the object name inside that image. So it runs a TensorFlow model to recognize what's in the image, and then returns the English name for that object. So you can see this first couple lines of code in that function. So it loads the image from the data, and it resizes the image to the 192 by 192. That's the size required by this particular TensorFlow model, and then it flattens the image into by flattening each pixel into a array called into a float array called flat image, and that's the input tensor into the TensorFlow model. So in this screen, we would see, the first line of the code is to read the model data. There's a specially trained MobileNet a TensorFlow model that we read this model data, and then we read metadata associated with this model, meaning this model is recognized and it is trained to recognize about 1,000 different images, objects in the images, right? So we have the English names for those objects in what we call a label map data. So that's a text file, and the next blocks of code starts a session, and as we can see here, it's a special. It has some special SDK functions that are relevant to the SSVM. So we call the SSVM TensorFlow interface, and we start a session with the model data, and then from this session, we pass in the input image as a tensor, and then tells the session what's the output tensor we expect to collect, and then we run and collect the output tensor. So in this whole process, we built up how we call the native TensorFlow functions, and then when we compile this to WebAssembly, the WebAssembly bytecode doesn't actually execute those. It calls a host function and passes the entire data and the commands into the host function. The host function then calls TensorFlow on that platform to perform this inference, and that's why the inference is done so fast, right? So after all this is done, we get another array about probabilities of each of the objects the probabilities for each of the objects occurring in that image. So so the image is so our model is trained to recognize say 1,000 images like cat, dog, things like that, and the return array contains the probability of that image containing a dog, probability of that image containing a cat. So it has a large array of numbers like that. So in the next slides, we do the post-processing of that probability array. We look into the array and find out what's the maximum probability, the line of the maximum probability, which that corresponds to what the model thinks the image mostly likely contain, right? So we find the maximum value and the line for the maximum value, and then we look up the label map metadata and find out what that maximum probability correspond to. For instance, we may find this image has 2% probability being a cat and 80% probability being a dog. So here we would print a dog, that we would be able to find that in the label map. So now I have shown you the whole process of preparing an image, the pre-processing, the AI inference, how to pass the pre-processed data into an AI model and run TensorFlow on it, and then get the return result, and then post-process the return result, and then go and return the data to the caller. So that's the whole process of using the WASI approach to do TensorFlow inference in WebAssembly. So here are some reference links to the code, the demo, and the tutorial. And so the things in the last slide, I want to talk to you about things we want to do next. So there's one of the strengths of WebAssembly is that the standard bodies around it, right? So there's a specification in the works called WASI Neural Network, WASI-NN, and that aims to accommodate not just the TensorFlow, but other tensor-based deep learning frameworks in the API that is similar to the one that I have just shown you. So we aim to fully support this specification that in the coming months, and we also want to provide different language SDKs. I have just shown you how to do that in Rust, how to have a Rust SDK to compile into WebAssembly to call the native host functions. We want to do the same for languages like Swift, AssemblyScript, and TinyGo. And by supporting WASI-NN, we can also support additional AI frameworks other than TensorFlow, as I have just said. And we also want to support more AI hardware. And so that's, I think my time's up. And hope you enjoy this talk. And if you like it, go to our GitHub repository and find more examples. And I hope we have used this approach to run AI models on edge devices and edge cloud. And I hope this talk would be helpful to you as well. And thank you very much. And that's the end of my talk. Thank you.